Hello, and welcome back to Quest. Or, if this is your first time, a special welcome to you. I'm your host, and today we're embarking on a journey through one of the most fundamental, yet profoundly mysterious concepts in the entire universe: time. We measure it, we feel it pass, we wish we had more of it. But what is it really? It's the invisible river that carries us from birth to death, the very fabric of our reality. Yet, the more we scrutinize it, the more its secrets seem to deepen, twisting our everyday understanding into mind-bending paradoxes. For much of human history, we assumed time was a universal constant. But then in the early 20th century, a patent clerk named Albert Einstein came along and completely shattered that idea with his theories of relativity. It's a malleable fabric interwoven with space itself, creating what we now call space-time. By two major cosmic players: gravity, velocity. Imagine space-time as a giant, stretched-out trampoline. A massive object like a planet or a star is like a heavy bowling ball placed in the center. The stronger the gravity, the deeper the well, the slower time itself flows. So time literally passes more slowly for someone standing on the surface of a massive star than it does for someone floating in the emptiness of deep space. It's not a feeling or a perception, it's a physical reality. The clock on your wrist would genuinely tick slower in a strong gravitational field. Have you ever wondered why it's 3 p.m. in London when it's 10 a.m. in New York? This wasn't always the case. Before the 19th century, time was a purely local affair. Each town set its clocks by the local noon when the sun was at its highest point in the sky. This worked just fine when the fastest way to travel was by horse. But then came the railroads. Suddenly, people were moving rapidly from one town to another. The chaotic mismatch of local times became a logistical nightmare, leading to confusion and even accidents. To solve this problem, a global system was needed. In 1884, representatives from 25 nations met in Washington, D.C. They agreed to standardize time by dividing the globe into 24 distinct time zones, each 1 hour apart. They also established the prime meridian, the line of zero longitude running through Greenwich, England, as the starting point for the world's time, Greenwich Mean Time, or GMT. Every experience we have tells us that time has a direction. Eggs break but don't unbreak. People grow old but not young. We remember the past, not the future. Newton's laws of motion, Einstein's relativity, quantum mechanics, something strange appears. Most of these equations are time-symmetric. They would work just as well if time ran backward. So why doesn't time flow backward in our macroscopic world? The best answer is entropy. Entropy equals sign measure of disorder or randomness. The second law, total entropy of an isolated system, can only increase. The universe began in a very low entropy, highly ordered state at the Big Bang, ever since it's moved toward greater disorder. This irreversible increase in entropy gives time its forward direction. It's the universe's tendency toward messiness that prevents the egg from reassembling itself. We're used to measuring time in seconds, minutes, and hours. A particularly fast camera might capture a moment in milliseconds. Those are thousandths of a second, or even microseconds, which are millionths of a second. Physicists need to probe events on timescales almost impossible to comprehend. They needed a new unit, the zeptosecond. A zeptosecond is a trillionth of a billionth of a second. That's a decimal point followed by 20 zeros and then a 1. To put that in perspective, the number of zeptoseconds in a single second is the same as the number of seconds in about 31.7 trillion years. In 2020, scientists were able to measure the time it takes for a photon, a particle of light, to cross a single hydrogen molecule. The answer was 247 zeptoseconds. This incredible measurement allows us to observe the inner workings of atoms and molecules in real time, actually watching chemical bonds form and break. We've talked about how gravity slows down time, but the other half of Einstein's relativity is just as strange. Speed has the same effect. The faster you move through space, the slower you move through time relative to a stationary observer. This isn't science fiction. It's a measurable phenomenon called time dilation. For most of us, driving in a car or flying in a plane, the effect is so infinitesimally small, it's completely unnoticeable. But for astronauts who travel at tremendous speeds for long durations, it becomes a real quantifiable effect. Astronauts aboard the International Space Station orbit the Earth at about 17,500 miles per hour. After a 6-month mission, an astronaut will have aged about 0.005 seconds less than the people they left behind. The most extreme example is cosmonaut Sergei Krikalev, who has spent over 803 days in orbit across multiple missions. He is, factually, about 1/50th of a second younger than he would be if he'd never left Earth. Long before the invention of mechanical clocks, smartphones, or atomic timekeeping, ancient civilizations had a deep need to measure the passage of time. They needed to know when to plant crops, when to harvest, how to conduct religious ceremonies. Their clock was the grandest one of all, the cosmos itself. The cycles of the sun, the moon, and the stars were humanity's first calendars and timekeepers. One of the earliest and most ingenious devices for tracking the day was the sundial. The ancient Egyptians were masters of its use. Some of the oldest known sundials date back to around 1500 BC. The earliest versions were simple obelisks or pillars that cast a shadow on the ground. By marking the length and position of the shadow throughout the day, people could divide the daylight hours into segments. Later, more sophisticated sundials were developed with markings that allowed for a more precise division of the day into hours. It was a simple yet profound technology, a direct connection between humanity's daily life and the majestic, predictable motion of our planet as it spins through space, turning its face toward our home star. You're probably familiar with the leap year. Every 4 years, we add an extra day, February 29th, to our calendar. We do this because the Earth's orbit around the Sun isn't a perfect 365 days. It's about 365.24 days. But have you ever heard of a leap second? It's a much more subtle and irregular adjustment, but it's crucial for keeping our clocks in sync with the actual rotation of the Earth. Our ultra-precise atomic clocks are incredibly stable. The Earth's rotation, however, is not. It's gradually slowing down over the long term due to the gravitational pull of the Moon, a phenomenon called tidal braking. To prevent our official time from drifting away from the Earth's actual day and night cycle, scientists occasionally add a leap second. When this happens, a minute will have 61 seconds instead of 60, usually on June 30th or December 31st. It's a small correction that bridges the gap between perfect atomic time and our slightly wobbly planet. We've touched on the arrow of time and its connection to entropy, but let's dive a little deeper into this profound mystery. Why does time seem to have this unbreakable one-way direction? Why can we have memories of yesterday's breakfast but no memories of tomorrow's dinner? This directional flow, from past to future, is one of the most defining features of our reality, yet it's surprisingly absent from the fundamental equations of physics. The hypothesis suggests that the arrow of time is not a property of physical law itself, but rather a consequence of the initial conditions of our universe. The Big Bang started our cosmos in an incredibly special, highly ordered, low-entropy state. Since that initial moment, the universe has been unwinding, moving toward states of higher probability, which are always states of higher disorder or entropy. Our ability to remember the past is a direct consequence of this process. Memories are records, ordered traces of events, which can only be formed as the universe moves from order to disorder. Timekeeping isn't just something we do with external devices. It's built into the very fabric of life itself. Nearly every living thing on Earth, from the simplest bacteria, plants, fungi, and of course humans, possesses an internal biological clock. These clocks regulate a vast array of physiological processes in a roughly 24-hour cycle. We call these cycles circadian rhythms, from the Latin circa diem, meaning around a day. This internal pacemaker tells us when to feel sleepy, when to wake up, when to feel hungry, and even when our body temperature should rise or fall. This remarkable biological metronome is controlled by a master clock in a part of your brain called the suprachiasmatic nucleus, or SCN. This tiny cluster of about 20,000 neurons receives direct input from your eyes. Light cues from the daily cycle of light and darkness synchronize the SCN with the outside world. This is why you get jet lag. Your internal clock is out of sync with the new light-dark cycle of your destination. It's a beautiful example of how life has evolved to anticipate and adapt to the most fundamental rhythm of our planet, its daily rotation. We began our journey at the dawn of time with the Big Bang, so it's only fitting that we end by asking, will time itself ever end? The answer depends on the ultimate fate of the universe, a topic of intense speculation among cosmologists. One theory, known as the heat death or big freeze, suggests that the universe will continue to expand forever. As it does, everything will grow farther and farther apart. Stars will burn out. Black holes will evaporate over unimaginable timescales through Hawking radiation. Eventually, the universe will become a cold, dark, and empty void, approaching maximum entropy. In this scenario, what happens to time? If the universe reaches a state of thermal equilibrium, Where there is no more energy flow and no change, has time lost its meaning? If the arrow of time is driven by increasing entropy, what happens when entropy can't increase any further? Some physicists theorize that in such a state, time as we know it would effectively cease to exist. There would be no before or after, because nothing would ever happen. It's a mind-boggling concept, a universe without change, a cosmos where the cosmic clock has finally and eternally stopped ticking. And there you have it, 10 facts that show just how strange, flexible, and profound the nature of time truly is. It's not just the steady ticking of a clock on the wall, it's a fundamental dimension of the cosmos, warped by gravity, stretched by speed, and driven by the relentless march of entropy. From the shortest zeptosecond to the ultimate fate of the universe, the story of time is one of the grandest narratives in all of science. It reminds us that our intuitive, everyday experience is just one small part of a much larger, more complex, and more wonderful reality. So what do you think? Which of these facts blew your mind the most? Was it the idea of time slowing down for astronauts? Or the theoretical possibility of its end? I'd love to hear your thoughts, so please take a moment to share your favorite fact or your own cosmic ponderings in the comments section below. If you enjoyed this journey through the mysteries of time and you're hungry for more deep dives into the wonders of our universe, then make sure you subscribe to Quest and turn on notifications. Thank you for lending me your time today, for your curiosity, and for joining us on this quest for knowledge. Until next time, keep looking up.